Hi, good morning. Today we are going to start the next section of chapter 9. So here last class we have discussed about closed graph operators. Here also one another example for a closed graph operator. Ax equal to dx by dt in L01 with the domain A equal to x belongs to C01 and x dash belongs to C01 such that x0 is equal to 0. It is actually not closed, but it admits a closure. So another example is A from L201 to L201 defined by Ax equal to x0 into t, domain of A equal to C01. So this operator also does not admit closure. For this, you can take a sequence x and t is equal to 1 minus nt. For 0 less than or equal to t less than or equal to 1 by n. 0 if 1 by n less than or equal to t less than or equal to 1. And we get ax and t is equal to, what is ax and t? Ax and t is x0 into t. So this is xn 0 into t, which is equal to, clearly it is equal to t. But what about xn? Xn t converges to 0 in L201. We have what about xn 0? Xn 0 is 1. Axn t is xn 0, here xn 0 into t, which is equal to 1 into t, which is equal to t. What about axn? What about axn is actually identity function on 0 1, same as identity. Okay, now norm of xn square is equal to this is L2 space. Okay, so here we are taking 2 now, and this is integral 0 to infinity. You can split like this. Okay, because from 1 by n to 1 the value is sorry, from 0 to 1 you can split that as from 0 to 1 by n and 1 by n to 1. From 1 by n to 1 the value is 0. Therefore we have to consider the integral from 0 to 1 by n only. Norm of xn square is actually is equal to this one, which is equal to this one. Simplifying, we get 1 by 3n. So xn converges to 0. Okay, but here we have axn txn converges to t and xn converges to 0. Therefore this operator does not admit a closure. Now moving to one of the important theorem, closed graph theorem. Okay, so the theorem says that let x and y be, listen carefully and it is very important, let x and y be Banach spaces. A from x to y is a closed graph operator and a domain of A equal to x. Then A is continuous. That means if A is a closed graph operator and a domain of A equal to x, then A is continuous or bounded operator. That is what we have to prove. Okay. Let x and y be Banach space and A from x to y be a closed graph operator. Closed graph operator means gamma of A is closed in. Okay, gamma of A is closed set in. So to prove this, what we are going to prove is we have to prove A is continuous. For this, we have to prove the result. We have a result like this. A function f from x to y is continuous at x if for every open ball u containing f of x, there exists a open ball v containing x such that f of v is contained in u. That is, suppose this like this, x and y. To prove f is continuous, it is enough to prove for f of x there is a ball containing u. You have to prove there exists a v containing x. This is containing f of x. There exists a v containing x such that this f of v is completely contained in u. Then we call f is continuous at x. So to prove here A is continuous, we have to prove it is continuous at 0, because as A is a as x and y are Banach spaces, if A is continuous at 0 implies A is continuous at x. So to prove A is continuous at 0, what we have to prove? To prove A is continuous at 0, what we have to prove? A is a map from x to y. You have to consider a point. What is A0? A0 is 0 because A is a linear operator. So you consider a ball in Y containing 0. Let a dy be that ball. And we have to prove there exists a V in X such that 0 belongs to V and A of V is completely contained in dy. This is we have to prove. So for proving this, what we are going to prove is we are proving 0 is an interior point of A inverse dy. For proving this, what we are going to prove is we are going to prove 0 is an interior point of A inverse dy. 0 is an interior point of A inverse dy means there exists an open ball V such that 0 belongs to V and V is completely contained in A inverse dy. V is contained in A inverse dy means clearly AV is contained in dy. This implies A is continuous at 0. This implies A is continuous at x. Okay. So here we have this one. Okay. F of V containing U. So 0 is an interior point means there exists a ball V which 0 belongs to V is containing. That means AV. So given an open set dy containing 0, there exists an open set V containing 0 such that AV contain. This implies A is continuous at 0 as it is a x and y are Banach space. A is a bounded we get A is continuous at 0 implies A is continuous at every x. So that is our aim. To prove A is continuous, our aim is to prove 0 is an interior point of A inverse dy. Okay. For example, there is no need to write all the things. You have to write these things only. Okay. It is enough to prove 0 is an interior point of A inverse dy. Okay. Now, to prove 0 is an interior point of A inverse dy, we are claimed that A inverse dy is a perfectly convex set. Okay. So, for proving A inverse dy is perfectly convex set, you take a bounded sequence xi belongs to A inverse dy. That implies AXI belongs to dy. AXI you can write as yi, that yi belongs to dy. And let alpha I greater than 0 be such that sigma I alpha I equal to 1. Then the series sigma alpha, we have to prove sigma alpha I xi belongs to A inverse dy. Okay. Now, what about sigma alpha I xi? Now, what about sigma norm of alpha I xi? Alpha I xi is equal to sigma alpha I into norm of xi because alpha i's are greater than or equal to 0. Therefore, this you can write like this. And xi, what about xi? Xi is a sequence in xi's are bounded sequence. Therefore, norm of xi less than or equal to k for some k. Therefore, k into sigma alpha which is equal to k. And we have this result. Let A and be a sequence in a Banach space X such that sigma n equal to 1 to infinity norm of A n less than infinity. Then sigma A n converges. Therefore, our sigma alpha xi is also convergent. Let x is equal to sigma alpha xi. Similarly, since yi is bounded, y is a Banach space, we get sigma alpha yi is also convergent. Okay. Let y is equal to sigma alpha yi and which belongs to dy because d is a perfectly convex set because any open ball is perfectly convex. Okay. Since A is a closed graph operator, we get Ax is equal to this Ax A into this, you can write as actually A of sigma I varies from 1 to infinity alpha I xi is equal to sigma uh, alpha I axi is yi, and sigma alpha I yi is equal to y. Ax equal to y, that means x is belongs to A inverse dy. Okay, since A is a closed graph operator, we get Ax equal to y, and sigma alpha xi belongs to A inverse dy, because y is equal to, this implies x belongs to A inverse dy, that means sigma alpha xi belongs to A inverse dy. Therefore, what we get, this a domain of A is also X. That means what we get, A inverse dy is perfectly convex. So as A inverse dy is perfectly convex, and what we get, we have 0 as domain of A equal to X. What we get, 0 belongs to kernel of A inverse dy. Domain of A equal to X implies 0 belongs to kernel of A inverse dy. By 9.1.3, if K is perfectly convex, then K interior is equal to KC. So 0 belongs to kernel of A inverse dy implies 0 belongs to interior point of A inverse dy, or A inverse dy interior. That means 0 is an interior point of A inverse dy. That implies A is continuous. Okay, hope it is clear. We have is this, you can write like this: Ax equal to y. It is Ax, actually Ax equal to A sigma I varies from 1 to okay. Now there is another remark. We have to prove closed graph theorem using open mapping theorem. So here consider the space E equal to set of all xy such that y equal to ax, which is a subset of x cross y, and the A has a graph closed. This implies E is a closed subspace of x cross y, as x and y are Banach spaces. X cross y is also a complete space. Closed subspace of a complete space is complete. E is also complete, I think. A is a E is closed. Okay. E is complete. I think E is complete. Okay. Now define u from e to x by u of xy is equal to x. Then norm of u of xy is equal to norm of x, which is less than or equal to norm of x plus norm of y. But this is a norm on ordered pair xy. Therefore, norm of u of xy less than or equal to norm of xy implies u is bounded. Since domain of Ax is equal to A equal to x, we get u is also on to, because if you take any y belongs to x, that means y belongs to domain of A. That means ay belongs to E, just that is in graph of A. Therefore, u of ay is equal to y. This implies u is on to. Now u of x1 implies x1 x2 equal to x2. This implies ax1 is equal to ax2. This implies x1 ax1 is equal to x2 ax2. Therefore u is 1 to 1. U is 1 to 1, and 1 to implies u inverse exists. X and y are Banach spaces. This implies u inverse is also bounded. So if you define a map T from E to Y as T of xy is equal to Y, then this is also continuous, and U inverse from x to y is also bounded. T from E to Y also bounded. Therefore, T U inverse from x to y is continuous map. Now, what is T U inverse x? T of U inverse x, which is equal to T of x ax, T of x ax equal to x. Therefore, T U inverse x equal to x for every x. This implies T A U inverse equal to A. This implies A is continuous because T U inverse is continuous. This implies A is continuous. Okay. So we can prove closed graph theorem using open mapping theorem also. Okay, that's all for today's class.